Next step is to introduce our speaker, Professor Renzo Ricca. He is a professor of mathematical physics of the University of Milano, Italy. His research interests include classical field theory, especially in the area of classical theoretical fluid mechanics, dynamical systems, including vortex dynamics and magneto-hydrodynamics, and structural complexity. He had obtained his PhD degree from the University of Cambridge, Trinity College. His supervisor was Professor Keith Moffat, one of the leaders, maybe not one of the leaders, but the leader of the area of topological fluid dynamics. He has been awarded many distinctions, including the Knight Prize, JT Knight Prize of Cambridge Uni, the Invitation Fellowship of JSPS of Japan, Visiting Scholarship of MIUR of Italy, and Lagrangian Senior Research Fellowship of Institute for Scientific Interchange. That is EASY. It is the short name for that is EASY, Italy. As well as some other visiting fellowship, visiting professor fellowship, and other things, distinctions. From the year of 2016, he has become a guest professor of our university, BJUT. So it is our great pleasure to have him to give us a 4-day short course about topological fluid dynamics. Here, may I have a suggestion for the audience? Please just write something on your book, on your notebook, because he will just give you handouts maybe 2 days after giving the lecture. So 可能在1-2天之后，他才能把那个他们手写的或者他们讲完全就是整理，非常有条理，然后我再发到群里。所以今天呢，可能大家还得稍微记那么2点，还得自己有一个记录，以免忘记。最终我们一定会把所有的东西都上传上去。还有呢，咱们今天大家也看到是有录像的，所以这个录像呢完成我会最快的，就是把录像散发给大家。至于能不能做到直播，我们再讨论。好，现在我们就邀请瑞卡教授给大家做报告。
Well, thank you very much. Thank you for the invitation. Of course, the Institute of Theoretical Physics in particular, represented here, and Xin Liu as part also of the Beijing Dublin International College. I thank you very much because it's a great pleasure to be here, and I know I've been always welcomed with heart, and that makes me very happy. So thank you for being here. So these lectures will follow the kind of new revolution that we are living these days due to the great achievements and the successes of recent approach of topological theory to physical sciences. You all know that this has had a great impact in string theory through the work of Ed Witten and others. And I am quite happy to tell you that this approach is actually much older. It is an approach rooted in the work of Kelvin, 1868, when he wanted to produce a theory of everything ante litteram, a theory of matter, exactly as we would call it now a theory of fundamental physics. He conceived the idea that vortices were like infinitesimally small particles. We could paraphrase that saying that is like a string in a fluid medium. It's like fundamental energy field at invisible scale. And the idea is extraordinary. The idea 1860s. He had the idea that a vortex ring could link or not in space. And because of the permanence of ideal fluid, no dissipation, then topology had to be conserved. First thing. Second thing, if topology is conserved, suppose you have a knot, and you have a different type of knot of different complexity, then the two knots had to have a discrete amount of different energy. So through this idea, he envisaged the possibility to interpret discretization of energy through topology. This is an incredible idea, 1860s, because he not only understood that through that thinking was possible to determine a spectrum of fundamental energy states, but he could also envisage the possibility that these states were independent from the metric. You see, so many ideas already there that we now attribute maybe to modern scientists. Okay, so we all know that this theory didn't survive. In the he had a number of outstanding followers, including J.J. Thomson. J.J. Thomson was an absolute brilliant mathematician in Trinity, and he worked on mathematical aspects of this vortex atom theory 20 years later, 1880. And the more he was working, and the more things came uneasy. And finally, he dropped the theory to become a physicist. And in 1906, he got the Nobel Prize in physics for the discovery of the electron. His first works were on the mathematical foundation of the vortex atom theory. So this is, very briefly, the story about the topological fluid mechanics that has gone shadowed, has gone down after that period because of the great successes of physics and the other interests in fluid mechanics, aeronautics, etc., etc., etc. But we inherit from that time this approach, the approach that through field theory, as we say now, we can investigate fundamental aspects, if not of the fundamental nature, but at least of nature. So I'm going to present you just the introduction to this field that is now very rich. These years, in the last 20 years, we saw very exciting new discoveries coming from very, very talented young mathematicians and physicists. And so this field that survived through periods of ups and downs is now resurrecting and having great impetus. Now I will draw your attention to a number of facts that are also relevant for mathematical problems, and I apologize if I will focus on mathematical aspects that are interesting for physical problems, but are more mathematical in character. So forgive me for this. Being a short course, I need, however, some background material, so I am obliged to start from scratch in order that everybody is happy with what we are going to do. And then pace will increase after the second day, so from tomorrow onward, we go a bit faster on more recent results. So forgive me if I start from really the beginning. And the beginning is material that you find in standard books, but has been revised. So I'm not going to present really the standard way of some of these topics. I will try to present you emphasis on aspects that are relevant later on. So I'm preparing notes, lecture notes for you. So I still have to prepare my last lecture, and I want you to have all the set ready. And since the set starts with an index, the index is not ready yet, and so please wait for a few more days, and you will have all the lecture notes. Now, the lecture notes contain full proofs of what I'm going to mention. So there'll be much more material than what I can present to you. I will skip some proofs. I will duel on some proofs, but in the notes you will have a much deeper presentation. So also historically, I told you what I wanted to say. There is a little bit more in the notes. I will skip some basic definitions, but I want to duel on starting from a theorem that is very important. Is not so important for the topics of topological fluid mechanics, but is a tool that has been very important in developing many ideas in this field, so I have to go through that first. But before going to technical aspects, let me just draw you a few pictures. And the pictures are stimulating our imagination. So suppose we have, I will be extremely unprecise at the moment, just to give you an idea of what we want to tackle. One problem is, for instance, something like this. I have to look at my pictures because I don't draw things very nicely sometimes. And we have something like this. And this gets linked with this part. And it goes back like this. Okay? Suppose you have something like this, and imagine that this is made of some material. Maybe plastilin. Okay? You can deform it. And you want to play with this material by deformation, continuous deformation. And you want to reduce this material to this material. Okay? Can you do this without any cuts? No. You think? No? Right. So the answer is that you can. You can, by continuous deformation of this material, imagine is plastilin, you can deform this to this. So this is a challenge, right? It's a challenge because it defies our imagination. We believe it's not possible, but it is possible. You can deform continuously, without cuts, this structure to that structure. And, well, one way to do it is to, you can deform this to make it very thick, okay. And then, well, we can use this to enlarge it a lot. We can make it very, very large, very, very large through here and here. Yeah? And then we can go this side all around the other and reduce this to this shape. I have a sequence here much better drawn than what I did, and I'm sorry you cannot see it, but it will be in the notes. So I prefer not to waste time, to leave you the curiosity to have a look at the drawing and step by step how to deform this to that. Well, there is another situation, continuous deformation. There is another situation where we may start with fluid, and we may put some light fluid on top. So suppose this is light fluid that stays on a heavier fluid. If we reverse the situation, this is stable, right? Because gravity, there's a pool of gravity working downwards. And imagine now that this part of the fluid is made by a heavier fluid. And for some simple reason, for simplicity, we assume that at a certain point this collapses. Okay? We know this. Oil and water, or vinegar and oil, etc., etc. We know that the two liquids, oil and vinegar, are hardly mixable. If we want to mix them, we have to stir them up a lot, to put a lot of energy. Okay, now suppose that this fluid is heavier, but not so much, so that after some time, as time passes, the fluid collapses here, and at a certain point floats on in the bulk of the other fluid, of the lighter fluid. Then there is a trace, and then this trace, as time goes to infinity, disappears. And suppose the fluid is heavy enough to be balanced by gravity at this stage. Then again, if you look at the situation at the beginning and at the end, with the fluid here that goes down like this as time passes, then you have a change of topology of this ambient space. Without cuts, how is possible? It's a continuous deformation. There is another famous example, and this is quite recent and has been done experimentally. And this, you imagine to drop something, a drop, and this drop goes into the water, and then there is a reaction, and you get a reaction from the water. So this is water, and there is a cusp forming. And by changing is air, and maybe some particular liquid. It's not entirely water. You may put some glycerin. You may change some particular physical properties of this, but you can get a cusp. A cusp. And this cusp can be infinitely thin here, with an extremely thin radius of curvature. These problems share a common aspect. One aspect is what in mathematics is called a singularity. singularities. Singularities. They share also the problem that in this case there is no change of topology. Here there is no change of topology under certain assumption, and here there is no change of topology except that there is a cusp, there is a point in space where the radius of curvature can be extremely small. Extremely small. How small? Oh, very small, 10 to minus something meters. So small that we go to scales of quantum physics, so that classical analysis gives you the wrong answer, because you get to a limit where you get wrong numbers for quantum aspects. You go below certain scales that are absurd. Now, all these problems share common features. Continuous change of shape without cuts, and emergence of singularities in finite time, maybe. So these aspects are central to modern research in mathematics, and indeed the problem of a singularity formation in finite time under equation of fluid dynamics is a well-known Clay problem of the Clay Institute. It's one of the 8 unsolved problems, or 7 unsolved problems of the millennium. It's a $1 million prize for this. Okay, so this is just to give you an idea that these are challenges and represent all these phenomena challenges for mathematics. So let's introduce some tools. First of all, I will focus on, to keep things simple, on ideal fluid dynamics, ideal context. Ideal is, of course, an idealization of the real world. But we may capture phenomena that, to a certain degree of approximation, are relevant for finer aspects. So I will assume a continuum hypothesis. Everything is continuous till a very small scale. How small? Any scale we like. Any scale. So, you know, the problem of viscosity. If you go below a certain scale, then can we define viscosity? Okay, so this is the first assumption, continuity. And associated with that, let me just sketch very briefly what I wanted to stress, is that we will focus on certain flow maps. So I will consider the motion of a fluid, say, from a point x0 to a point x, and x0 denotes the initial position, x will be at a certain time, and this is a flow map that transforms a structure, a vortex, a magnetic field, something, brings a point in the fluid to the new position. Now, this flow map, I constrain myself to work in a set of flow maps that are like this. I take these flow maps to be continuous, smooth with new large enough, so that we have a inverse map, phi minus 1, that gives me x0 through the inverse map, x and t, if we have t. And this is for any t finite, in a finite interval.
Excuse me, Renzo. The first one is C to gamma or C to W?
To nu, to a number.
A number.
Yeah.
But smaller than infinity.
Yes.
Okay.
Yes. Now, this means that we can always go back to x0, right? We had this problem of the cusp, huh? Remember, each point, when the surface produces this cusp, each point of water goes up, 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 and at a certain point, we should be able, from this phi minus 1, to distinguish here every single point that collapses to one point, which contradicts what I said. You can reverse this experiment with the usual experiment, you know, tap water. Tap water. You shut up the flow of water, and at a certain point from the water forms a drop. And there is water here. At a certain point, the drop starts to detach from the fluid. What happens to this point? This breaks down. We have no longer inverse mapping well defined. We have problem with the inverse map. So you see, as we define our fluid to be continuous with the inverse that exists at all time, we immediately cut out many important problems. Many important problems of real life, but also mathematically. Mathematically. Here, we may have problems for a singularity, for the inverse of the flow map that is ill-defined, or even worse, in some natural circumstances, we have, instead of a cusp, we have an angle. And an angle is, to some extent, is same problem. Where is the tangent at the angular point? Is ill-defined. We have a problem there too. Okay, so I will confine myself.
There's a singularity. Why it must be a singularity? It can be a step or
Oh, sure.
Why it must be a singularity? It can be.
It can be perfectly well defined. Yeah, I know. It depends on the context. It depends on the context.
Okay.
So Renzo, what you are thinking about is we just study the period that topology is conserved. So that just means the very moment topology changes. So we just throw away that case.
Exactly.
We only consider the perfect.
What I'm saying is that what you will see, we take this as our working set of flow maps, and by doing this, we cut out many problems that we don't know how to handle. Let me go back to the point. Suppose we have two field lines that intersect exactly. What is the physics there? What is the mathematics there? Can we talk about the tangent at a point there? This is a normal problem tackled by many contexts of physics. It's called reconnection. The state of a field line that goes through the other at the instant of the intersection, there is difficulty to tackle this problem because we don't have the mathematics. So my emphasis here is that we are using old-style mathematics, but we need also to think at the same time of something new in mathematics, to have new techniques to handle these problems, problems of singularities that are associated with changes of topology. Okay? Before I mentioned in the first diagram, I told you there is no change of topology. It's continuous deformation at all times.
Definition of singularity. What is singularity?
What is a singularity? It depends on the context. It depends on the context. Yes, depends on what you're talking about. I mean, there are many ways to talk about singularity. For example, when this breaks down, when the inverse breaks down, when there is no inverse to the flow map, then you have a singularity. Because you cannot identify, suppose you have a system like this, two field lines, that at a certain, suppose you orient these field lines, and suppose that now they touch, this is in space. Can you go back to here, or can you go back to this situation? Which one?
this is maybe previous time, this is after time, or the other way around. But there is no way to know it from this, because you have no inverse.
So that's the key point of singularity.
Yeah, is one of the key points of singularity. Yeah, losing the inverse. And so it's a diffeomorphism, is a continuous deformation that is differentiable at all times. So diffeomorphism, but the diffeomorphism may not have the inverse map. All right, so this is just a little preamble. Okay, let's start with the first tool. I told you we are going to use some tools. I have no time. Everybody is at home with the concept, of course, of velocity, of acceleration. Acceleration, we know how to define acceleration in space and time in classical physics. I will use this notation d for the total derivative of a quantity. Suppose that I consider x as my space variable, and I consider this dx dt, then dx dt will be, if x will be a function of, say, a arc length and time. Suppose I go to velocity, okay? I take acceleration. It's the same thing. Suppose I take the velocity u, and u is function of x and t. Then I have acceleration a, defined as du dt, and this du dt is given by two contributions, as you know. We have a contribution in terms of time and a contribution in terms of space. All right? Are we happy about this? We have u dot grad u. This is called the temporal derivative. And this is convective or transport derivative. Okay? This is standard. Yeah?
Just an interruption. I have to tell the students, your underlying u is our u, the vector.
You use this notation, perhaps.
We use other notations. Yeah.
Yeah?
This is our Chinese.
Okay.
Right.
Okay? All right, I will use this one. I'll try to use that one.
That's okay. No worries, we can follow you.
All right.
And your capital just means proper.
This is, this is the total derivative. D dt, total derivative with respect to time. Okay? So this is important, right? Because there is a nonlinear part and the linear part. This is the transport of u and in space, and this is the transport, so to speak, of u in time. One other basic notion is the notion of field line. So I will stick to u. U is the velocity field. Velocity field. This, as I said, is acceleration. The other fundamental concept is the concept of a field line. So let me use velocity. I will call streamline. I will call streamline a line in space in R3, where at each point u is defined to be identified with the unit tangent. Okay? So if we prescribe the unit tangent at each point of this line, say this line C, we have the unit tangent t, t hat, because it's unit, and t hat is made of 3 components, t1, t2, t3. Then u will have 3 components, little u, v, and w. Then the definition of a streamline, a velocity line, is simply given by u over, if you like, dx over u equal dy over v, and this is equal to dz over w if the space x is given by x, y, z. This is the definition of a streamline, okay? Now, notice that we may divide everything. We may divide everything by ds, where s is a coordinate here, and we get the dx ds as t1, dy ds as t2, and dz ds as t3. So we identify, as I said, the velocity u with the unit tangent t. Okay? So this is a vector field line. I use it, the word streamline, I use it for the velocity. I can use any vector field. Magnetic field. So how do I define a magnetic field? The same thing. Okay, I have a B, the magnetic field, that is identified with the unit tangent on a curve C in space. I'm cutting short a little bit of introductory notes on this. So field lines will be very important for us. We will talk about the collection of field lines. And now I'd like to introduce you a kinematic result due to Reynolds. So this is a kinematic transport theorem. This is useful because we want to apply this derivative, the total derivative, to quantities, for example, mass, that are defined through an integral. Okay? Mass is just the integral of the density over the volume. And we want to use this derivative on integrals, on integral quantities. So we want to know how this quantity works. Okay, so we need this theorem. And the theorem, I want to give a little proof of this because it's so fundamental. So is based on, is a development of Leibniz rule. So it's not so extraordinarily unrelated with the typical integration. So the theorem says the following: let G, a certain quantity, function of space and time, we are in R3 of course, be some fluid property, unspecified for the moment, and we take it per unit volume. Then the standard derivative, d dt, of this quantity g of x and t in d3x. Sorry, you follow me if I keep using this, otherwise I tend to confuse myself continuously.
Per unit volume.
Well, for instance, it's not so necessary at the moment. I just want to show you that what we are going to do is that this derivative enters here, and we have a partial derivative dg dt over the volume d3x plus the surface at t of this volume g times, of course this is always the same g, times say w. W is like a velocity. At the moment I'm not thinking exactly as a fluid velocity u, That's why I use a different letter. It's just a theorem of kinematics, of mathematics. It's not of physics. I will apply it to physics in a moment. Some velocity v, unit vector nu, normal to the surface, d2x. Okay, so this, I will give you a little proof of this, because we need this, and after this proof, we can move quickly on applications. So the proof of this is just rather elementary, and you have to consider the volume, and this volume is function of time. It changes, and as time changes, t, then there is a new surface that is formed at time t plus dt. So the proof of this is rather simple. You have the integral of g, v on d3x, and this is at time t plus dt. Okay, because we want to construct the differential dt working on this system. So we have the integral on the volume that has now changed t plus dt of this g that is now x and t plus dt in d3x. And this is the integral of vt plus dt of what? Well, we expand, Taylor expansion. Well, it's normal. In books, everybody does this. We Taylor expand. This is the very first time that I have to stop, slow down, and tell you, remember, we Taylor expand. We assume that we can Taylor expand always. Remember that problem of singularities, etc., etc.? You see how creeps in the fundamentals of what we are doing. We just started a few minutes, and we already noticed that we expand, we will have a tool, we use this tool, everything is fine, books and books and books, but if here we have a problem, because there is a singularity somewhere, immediately we have a problem at the foundations. In the tools we are going to use for the rest of the course. Okay, so we Taylor expand that, and this is g of xt plus dg dt xt plus, well, we can, dt, sorry, dt plus an order of magnitude of this dt squared. Okay, something like this. And this is d3x. Now we need to evaluate this integral, and so the v at time t plus dt is, so this I will call it just the volume, just to focus on this part, and this is just the integral on dv of v of t plus the contribution, the variation of vt in dv. And this is just the integral on dv of v of t plus. Now this variation, the variation of the volume is due to the variation of the surface, and so we have to take into account the surface contribution. So we have s of t, and this is just some velocity v, not necessarily the fluid velocity, because the volume may deform due to some other reason. So v, which acts on the unit vector that I assume is pointing outwardly. So let's say nu. Okay? And this is d2, ds. Okay. So we put all this together now. So we have integral of g over the volume v, x and t in d3x. This becomes, this is at t plus dt. This is the integral vt of, again, the Taylor expansion we used before. let me write it as G plus dg dt in dt plus the order dt squared. And this was on d3x.
Why don't we use the stochastic?
Not yet. It will, yeah. Yeah. Okay, and then we have what? We have, this is on V, and then we have to move on S. So we have plus integral S of t dg plus dg dt in dt plus the order dt squared, and this is d3x. And now we can conclude the integral over v of t g plus the higher term contribution vt dg dt in d3x plus the surface s t g times w dot nu. I will emphasize, I will put it in this form over there. And this is ds, just to keep things differently. And this is dt plus an order dt squared. You know what I'm going to do. I'm just taking the limit. So I'm taking the limit. I have t, I have v at t dt, and then I'm doing minus the v at t as delta t goes to 0. So we have the following d dt of integral of g, exactly the statement, d3x over v of t. This is the limit as delta t goes to 0 of 1 over delta t of that difference. And that difference is the integral on v of g d3x minus this calculated at t plus delta t minus the integral on v of g d3x. Okay? And this is calculated at t. So we proved this statement. Okay? We proved this statement.
So the second line of that line.
This one?
No. One line up. Yes. That one just comes from the last term of your.
Yes.
That one.
Uh,
But how to follow?
This comes from here. This part here comes from here. This part here is just I'm grouping up G. I'm grouping up dg dt here and in G in ds, if I'm correct. Let me see if I might have escaped. Sorry, I lost on the notes what I've done. Okay, here, and this in dt plus the rest, yes.
So that means your w dot we had,
Yeah,
it is the argument of G, capital G.
yes. Yes, this is, I omitted here all the expansion.
Yes, sure.
Yeah, I just showed that that part is due to the movement of the surface because the volume changes. And then I apply this argument to the G expansion, omitting higher order terms. Because this is a d2, ds is a d2x in dt, so it's higher order and higher order.
So in your theorem here, it should be w dot we had.
Oh, sure, sorry.
Yeah. And yes. That is
Okay.
argument of G. Yes.
Yes. Ah, no, 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 no. This is just the product of G times the scalar product of V nu.
What's the W here?
W is is arbitrary at the moment. It will be velocity field. At the moment, it's just a field that makes the volume changes. So imagine that the volume is subject to motion that is not necessarily coinciding with the fluid motion. You may have a fluid that behaves, suppose is charged. Then particles go in one direction and the fluid goes in the other. The fluid has a velocity u, and the particles may react to some electric field or magnetic field. So for the moment, it's just a vector field. Then, for simplicity, we identify this vector field with u. I can do it instantly in a moment. And then you give a sense of this change of volume due to the motion of the fluid. A fluid that is not electrically conducting, I'm not considering magnetic fields, I'm not considering electric fields, I'm just considering neutrally charged, if you like, neutral fluid. Okay, let me remind you, well, if you take this theorem and you consider I want to leave it there, and I want to just give you the idea that you may now consider V as a material volume. Okay? A material volume meaning, in fluid mechanics, a volume made by the same particles all the time. Imagine that you color with ink this particle, or this particle are like coffee powder, then they remain the same in the volume. The volume is a material volume, so that these particles that have a certain property, for example, are colored by blue, they remain always the same with the same blue. This concept is very important and useful because we will talk about field lines that remain with the property of being streamline, of being vortex line, of being magnetic lines forever. Made as material lines, but the same properties all the time. So if V of t denotes material volume, then, of course, we can extend this, and V coincides with the fluid velocity u, as I give it before, then this immediately becomes the transport theorem for classical fluid mechanics, where V is a material volume. So we still have the same. Now the ddt becomes, the ddt in this case becomes d dt of g of xt in d3x, volume Vt, and we'll almost the same with this exception of understanding that now u is the velocity field, and the V is a material volume. Okay? St, and this is G times, for the moment is a scalar. It's still a scalar, but I will show you, we are going fast now. G of u dot nu d2x. d2x is ds over there. So from here, we get to this. So the kinematic transport theorem for fluid mechanics becomes this one. And this one is a very fundamental tool because you see how it works. You take the Lagrangian derivative of a quantity under integration, and you're allowed to perform partial derivatives inside. Remember, Vt is changing, but is made by the same particles. And these particles are moving according to the velocity u. Okay? So this tool is fundamental in doing many derivations. Now, I will be quick, because this is the hardest point. When we are here now, we can use this tool, and you will recognize immediately this tool in many derivations. In many derivations. I will use this tool if G is a scalar quantity, as it is now, and represent density. We know that mass is conserved, and I will apply ddt of this quantity of mass to show that there is no change of mass in fluid, and we get the conservation of mass immediately. That is one fundamental equation we will get to, continuity equation. But before doing this, I want to show you, I want to mention, not to show you, but to mention that if, I'm not going to do it, it's trivial, it's very simple. Imagine that you have a fixed unit vector in space, fixed, okay? You choose a vector in this direction of unit length, and you multiply this vector through this equation, all through. So you get inside, because it doesn't depend on time, is fixed, and you get g times this unit vector. This g times a unit vector becomes, I'm now moving, becomes this g. Is a g with a unit vector. And the unit vector goes inside everything. So you immediately have a theorem after the theorem we had for a scalar quantity. We have a theorem for a vector quantity. Actually, even more. If this g we put, for fun, 2 hours, 2 hours is just not the standard mathematics, but I'm just playing with symbols, just to remind you that not only we have the theorem for scalar, we have a theorem for vectors, we have a theorem for tensors, for tensor quantities. It's the same thing. Why? Because we just go through multiplication of something that is fixed in space and time. So, is a way to prove that this theorem holds for any quantity in any dimension. Good. This is a starting point. We have a tool to use for a quantity that is either a scalar, a vector, or a tensor. Now, surely you noticed here we have a surface integration. Surface integration. Come on, one of the first things you have to remember in standard background education of math for physics is to use what Gauss discovered. We have an integration of a surface, so we have we can convert this into the divergence, right? It's called the divergence theorem, because the nu on the surface gives you a direction along which you act. So you have a flux through the surface, a flux through the surface, and you use divergence theorem. So you can convert this surface integral into the divergence equivalent of it. All right, so we do that. So already you saw quickly, once we got this result, how quickly we can now get this total derivative working on integral quantities, scalar, vector, tensors. And now we do one further step. We transform this by using divergence theorem. And then we are almost done, because we have a tool that is working throughout fluid mechanics, repeatedly. Remember that we had to go through this Taylor expansion at a point? Okay, so these two features. One is there is a little point that is, so to speak, not so worrying, but it's worrying if you have a different frame of mind. And the other point is that you have a tool that is very powerful, and you get all the theorems in, basically, all the fundamental theorems in fluid mechanics. Let me show you how to convert that into the divergence form. Yes?
In the upper level, you have both the small ddt,
Yes.
the capital DDT.
Yes.
Are they the same? They are both total derivatives of time.
Yes, but this one, so this is a material volume, and so you can convert the standard derivative, the ordinary derivative, with this one, because you consider the Lagrangian. You follow Lagrangianly. I skipped, of course, difference between Eulerian and Lagrangian coordinates.
Is it like the green function?
Pardon me?
Green function for this.
Green function? We get to green function. Yeah, because you see the G. No, it's not quite there. We get to the green function.
Is a map from your real space to the momentum space. But
Green function is also a singularity function of the singularity.
Sure. We will. I'm going in that direction. Yes. Tomorrow, not today. Tomorrow will be green function time and singularity time a little bit. All right. So.
you mean, excuse me, you just skip the Lagrangian and the difference between the Lagrangian and the Euler.
Ah, okay. So this is important. Is a fundamental aspect. Okay, I have to invent a way to explain this. One way to explain this, or to remember this, is the following. Suppose, I don't know, suppose you have a river, and you have a boat here, and there is a bridge over this, okay? And there is a bridge, and this bridge, there is a person here looking at the boat, and the boat, there is another person there. And this person, we call it Euler. Euler. And this person, we call it Lagrange. I hope it works. I don't know, because I'm improvising. Sometimes it doesn't work. Euler is, you have WeChat, right? So is WeChatting, is sending information to a friend. And maybe Lagrange is a beautiful lady. I don't know, is a beautiful man. Who knows what? And Euler wants to say, I'm seeing Lagrange going away. So he's sending information about Lagrange. Coordinates. So the coordinates, this position is the Eulerian position. And as time, suppose the boat goes in this direction, as time goes, this is signaling the position of Lagrange. Okay? But Lagrange has a different view. Lagrange, moves with the fluid. Imagine that Lagrange is not really on a boat, he's on a molecule of the fluid. He's floating. So the information that Lagrange with WeChat to somebody else is sending is the reference, the distance from here. So Euler gives information in terms of as time changes and coordinate changes. But Lagrange gives information in terms of the initial position. The initial position, x0. I was here, and now I'm moving away from here, or from some reference point, from where Euler is. So all the information is x0 and t. x0 is the initial point, and from that point, initial time t0, the initial position, and from that initial position, he sends the information as, so you have to know how the motion is with respect to some initial position on a molecule. That is very bad for computational reasons. For computational reasons, it's very bad. That's why Lagrangian mechanics developed up to a point and then was dropped, especially in this last century, because you want some reference fixed and the motion taking place in your numerical box. But if you want to follow the powder of coffee, you are on the coffee powder, and you see all the world around you moving. That is very, very hard. That is very hard to report back the information. It's not very hard in principle. You are there, you're moving. We are on this planet, and we see all the universe around us that somehow is moving, so to speak. But if you want to report back with respect to some reference frame, fixed reference frame, is hard, because you have to know this and you have to construct the map. You have to know the map at each time. It's much easier, this one, because you measure the position at each time. But here you have to have an inverse map all the time. So this is the Lagrangian viewpoint. This is the Eulerian viewpoint. And then is reflected when you integrate the equation. You may have a velocity. You want to integrate velocity in order to have position. When you integrate velocity, then you have to take care of these two approaches. One is just integrating with respect to time. You get immediately the position. And the other one is not enough, because you have to know the function that depends on x0. X depends on x0. So this is more complicated. So this is the view. We often, in many aspects I will present you, we use a Lagrangian viewpoint. I told you it's not fashionable. It's not fashionable because computationally is very hard. Why we use a Lagrangian viewpoint? It's simple. Because I want to stay close to the structure, say a vortex. I want to be on the vortex. I don't care if the vortex hits the river, hits a building. Meteorologists care about that. Meteorologists want to know if the vortex hits a building. So they have to have a reference frame fixed. But I want to stay on the vortex. I want to see how the vortex evolves, change its shape. Okay? So I will be moving Lagrangianly. And all I'm going to say will be on these structures. Suppose we take a magnetic knot. I want to see how the knot changes shape is staying on the knot and not outside the knot, not with a fixed reference. So this was very popular at a certain point with a number of people. Some, for example, Cauchy was keen on Lagrangian coordinates, and Lagrange was not keen on Lagrangian coordinates. Both are due to Euler. So it depends. When you use, say, the Cauchy approach, you find quantities that you may see invariant properties. Because you move, I move on this planet Earth, and I recognize this planet Earth as my home. I know the structure of this planet Earth. I know everything of this planet Earth. I can see if it is changing or not, if it is breaking up or not. But if I'm away and I'm studying a planet, I have to report back this information all the time. So invariant properties are easier to study Lagrangianly, because I can see staying on the structure if it changes some topology, for instance.
So is a Lagrangian frame inertial frame or not?
Is not.
Yes, Euler's.
Euler is.
Yeah,
definitely.
Yes. Okay.
You have to have this flow map, the inverse of this flow map all the time. That makes problems in reconstructing the position, because what you're thinking now is Eulerianly. You think as an Euler. You want to know this boat where it's going. But I don't care where I'm going. I'm caring if the boat breaks up or not. I want to stay on the boat, and I can reconstruct the motion close to the boat with respect to the river I was, with respect to the shore, to the bridge, to some reference. But sometimes I don't care. You see, I may not care. I may not care. If you are away in the sea, you may want to take care of your boat if the boat is working fine.
So you're considering kinematics, not dynamics?
No, at the moment it's still kinematics. You're right. Yeah. We get to dynamics in a moment.
Can we say the viewpoint of Lagrange is more natural? It is consistent with the theory of relativity, and Euler's point is consistent with F space-time viewpoint of Newton.
I'm not so sure about that. Because it depends on the problems. Certainly, if you I rephrase it my way. If I'm considering invariant properties of an object, say the boat, then I am Lagrange. Because measuring changes here can tell me if these changes are occurring or not. But if somebody wants to know here what changes are occurring here, you see what I have to do? I'm moving. All the changes I have to tell this changing to this person in terms of the distance from the bridge. I have to add some more information because I'm caring about the bridge now. So I need this flow map inverse. I want to say the boat, is taking water. This is a change. And with respect to the distance. But if I care about the water, if the boat is taking water or not, I don't care about the distance at all. I just care about if it takes water or not. If it doesn't take water, I'm happy. And suppose I don't want to go anywhere. I just want to float. Suppose. Then it's okay. The boat is fine. I'm not taking water. I don't know. I'm not quite sure where I'm going, but it's fine. But if it's taking water, I need help. I need to communicate my position, and I need to communicate how much water I'm taking in. And the people that listen, they have to compute two things. The water I'm taking, and if I'm going away, where I'm going to be with the amount of water I'm going to take, because I need two informations. So, of course, if you are helping somebody, it's easier to have Eulerian viewpoint. The Eulerian viewpoint means you are mapping from a fixed reference frame whatever happens. From here, I just need to know if there is water or not. So suppose this is the example. Suppose the water is empty and is floating well. This is the invariant property I want. If I'm taking water, this is no longer conserved quantity. And so this is not invariant with respect to motion. Of course, it's not invariant also in Euler terms. But in Euler terms, to have the same amount of information, I need just more information. Because I have to report back all the time. You see the difference? So computationally, it's much more advantageous to stay here and to see what happens. Because computationally, if you are Lagrange, you have to calculate. You have to have a reference system here that calculates your invariant properties, and then you have to report back. But to report back, you have to know the evolution of the fluid. There is a similar problem. One of the first problems I considered when I was your age is exactly of this type of problem. At the time, there was a beginning of string theory. And my first paper was actually in this context. It was the emerging string theory of the time in the 80s, late 80s. And the string was a vortex, a la Taubes. And these vortices could be studied either with a reference frame on the vortex or from outside. And so I started to consider the Lagrangian viewpoint, to stay on this string. On this string, you see the motion and perturbation of the strings, but then you have to report back sometimes.
What you read, the dynamics is depend on what you choose. Depend on Euler or Lagrangian
Or both.
universe.
Yeah, you can choose both dynamically.
The dynamic function is the same in both.
Is not the same. Is a composition of functions.
From as a physical
Oh, of course. Oh, sure.
We should write only one equation.
Sure. It's the same. It's the same because you can transform one system into the other. So in principle, it's not a problem.
So the Lagrangian one should have an extra term containing some.
The Lagrangian should have information about the initial position all the time. Is the very first mapping I gave you, this one, x0 to x. And I have to know this map, and I asked for the existence of the inverse at all times. That saved me.
But
That assumption saved.
That one is not an inertial system, so you should have an extra term.
Oh, you have
Containing some acceleration information.
you have extra terms. Yes.
Yes.
It reminds me
Some
of.
accelerations.
Yeah, you know better than me because it's not my field, but is what is called Thomas precession. You know, Thomas precession is when instead of the electron, you are the system of reference is
Yes.
yeah,
Precession, yes.
yes, is Matteo now is taking care of that problem. Yeah, so this problem will accompany us, and I will have time to make more comments. Because, of course, a vortex will induce a motion, a fluid motion. And it depends where you are. If you are on the vortex or if you are on the fluid. Of course, the physical phenomenon is the same. But the way you perceive dynamics is different. The way you perceive it.
As well as some so-called Coriolis force.
Yeah. Okay. So I want just to, so this is a little story about Euler. So remember, Lagrange is on a molecule and is moving. And Euler is fixed and is looking at the world that is changing. Okay, this is just helps you maybe to remember these two. And this is the so-called Lagrangian derivative, because it combines together the time variation and the space variation. We will come back to this because it's important. When you say that something is constant, it's constant with respect to this variation. It doesn't mean that it has constant value. It means that the sum of the variation in times and space balance out. Okay. All right. So, of course, we have the quantity from this. We can say a corollary. The corollary is that if V of t is a material volume, then derivative with respect to time of this quantity g, as I said, it can be a scalar or a vector. At the moment, it's still a scalar, if you like, is just the integral Vt of dg dt plus, I apply divergence theorem to that one, and I have the divergence of gu. in d3x. I transform the surface integral into a volume integral, and this is just the basic relation.
Can we have a break?
Yeah. One last step is just easy on the blackboard to do it. Please repeat the exercise of multiplying everything by a fixed vector, and then you immediately transform the same equation into an equation that works for a vector. What we'll do, we use these dual aspects. When G is a scalar, we use mass, and we apply this. And when G is a velocity itself, we get the conservation of linear momentum. I stop here for the moment. We take a break, and then we resume.
Thanks.
Okay.